Okay, good day, ladies and gentlemen. So, we're going to talk about character encoding. We're going to talk about the ASCII and Unicode character sets, and we're going to talk about how do we go about calculating the amount of space that we need to store character data. So, if you remember, a couple of weeks back we talked about there are different types of media, and that we have character media, image media, audio data. And we need to be able to get that into our computer. And we use the word transform. So we're going to take an image and transform it into zeros and ones. Instead of transform, I want us to use the word encoded. Okay, we are going to encode character data. And that means that we take our character data, whatever it might be, and then we encode it into zeros and ones. Think back to 1960s, early 1960s. There were computers, probably didn't even have a monitor at this point. There were computers, and to get the data that the computer was calculating, they'd have a printer. And the computer would just print straight out to the printer. The problem that was faced was, well, how do you get characters onto a printer? So what was decided is there would be a universal table that all computers would know about, of 128 characters, and each number would have a dedicated character. So if I wanted to print the letter capital A, I would send 65 to the printer. And if I wanted to print the capital, or if I wanted to print the lowercase m, I would send 109 to the printer. And so this was a way for computers and printers to be able to speak to each other. ASCII is the American Standard Code for Information Interchange. Originally was 128 characters, so 7 bits. And then later they extended ASCII to 256 characters using 8 bits. Okay, so the way you read an ASCII table is if you are looking for a character, so for instance, all of these characters down here are specific to a printer. So for instance, LF means line feed, so that would move the printer down to the next line. CR means carriage return, so that would turn the printer back to the left hand side of the page. If we wanted to send the word Sala in capitals, you would say, right, or where's S? S is 83, so you would send 83. Then where's A? A is 65, so you would send 65. 76, 73, 72. You'd send those codes to the printer would take those codes and convert the numbers into the individual characters and then print out each individual character. So ASCII was fine for many years, but it does have some limitations. So 256 characters is actually not a lot of characters. By the time you start adding things like punctuation, numbers, different accents, you very quickly run out of 256 characters. It also meant that there was no support for Arabic, Mandarin, or other non-Western alphabets. And there was no support for things like currency symbols. I mean, there was dollar, but there wouldn't have been things like euro or other math symbols, for instance. So there was a lot of limitations to ASCII, which is why then that we developed something called Unicode. So Unicode is exactly the same idea, where different characters have a different code, but instead of there being 256, there's 128,237. So basically that translates to being 16 bits per character. The reason you probably use Unicode, or the reason you probably know about Unicode, is because it allowed the invention of the emoji. When you send your friend a emoji, what you're actually sending is the Unicode number for the emoji. You're not sending an actual image, you're just sending the code. And then your friend's phone takes that code and interprets it and decodes it and then sends it back to being a emoji. And you can see this by, if you open up a Python REPL and type this in, you'll see a Python emoji. Python gives us two commands that we can use to help encode and decode our data. The ORD function, if you put in a text, if you give it a piece of text, then it will tell you the ASCII number for that text. And the CHR function does the opposite. So if you put in a number, 65, CHR65 will give you the letter capital A, because that's its ASCII equivalent. That's the first part of the video, ASCII and Unicode. You also need to be able to calculate how much space some character data is going to require. And it's pretty straightforward, basically. All you need to do is to multiply the number of characters times the bits per character. Okay, so that's pretty straightforward. The bits per character will depend on whether or not you're using ASCII or Unicode, because ASCII uses 7 bits if it's basic or 8 bits if it's extended, and then Unicode uses 16 bits. So Sala in ASCII, it would be 5 characters times 7 bits, a total of 35 bits. Sala in Unicode would be 5 times 16 bits, which is 80 bits altogether. Okay, and if you think about a book, a very famous book, War and Peace, known for being an incredibly long book, War and Peace has 1,225 pages. You can assume it's around 100 words per page. Again, assume 10 characters per word. So how many bits would be required for that? Well, that's 125 pages times 100 words per page times 10 characters per word times 7 bits each would be a total of 8,575,000 bits. Right? Once you work that out, that's about 1 meg. The background image that I store on my desktop is 4 meg. The photos that you take with your phone are 12 meg, probably. So you can see how little data, text data, character data, how little space it actually takes. We can take a huge book like War and Peace and store it in a quarter of the space it takes to store the image on my desktop. Okay, so that's the character encoding. Just to recap, ASCII, there are 127 characters in basic ASCII, there's 128 characters in basic ASCII, 256 characters in extended ASCII. There are various limitations of ASCII, so then we developed Unicode. There are 128,000 characters in Unicode. And the way that you calculate space is characters times bits per character. Okay, as always, if you have any other questions, feel free to contact me, and I look forward to seeing you all soon.